Hello everyone, welcome to this exploration of a fascinating area of mathematics. Today we're diving into the world of differential equations. These equations might seem intimidating at first glance, filled with strange symbols and notations. But don't worry, we'll break it all down step by step. At its core, a differential equation is an equation involving a function and its derivatives. Think of it as a mathematical relationship between a quantity and how quickly that quantity is changing. It's a way of expressing how things evolve over time or space. It links a quantity to how it changes. This connection is what makes differential equations so powerful. They allow us to describe not just the state of something, but also the process by which it reaches that state. This lets us model dynamic systems, not just static ones. We can analyze systems that are constantly in flux, where change is the only constant. From the flow of water to the swing of a pendulum, differential equations provide the tools to understand these dynamic behaviors. For example, a regular function might describe a car's position, telling you exactly where it is at a given moment. But a differential equation connects that position to its speed, its rate of change. It tells us not just where the car is, but also how fast it's moving and in what direction. This information allows us to predict where the car will be in the future. This is the key idea, describing not just where things are, but how they evolve. It's about understanding the underlying mechanisms that drive change and using that understanding to make predictions about the future. Why does this matter? Why should we care about these seemingly abstract equations? Because everything around us is changing. The world is a dynamic place, constantly in motion. Populations, temperatures, all are subject to change, growth, and decay. Understanding these changes is crucial for making informed decisions and solving real-world problems. Chemical reactions, planetary motion. These phenomena are governed by underlying principles that can be expressed using differential equations. Differential equations are the language we use to describe and predict these changes. They provide a framework for understanding the complex interactions that shape our world. They're foundational in physics, engineering, providing the tools to design bridges, analyze circuits, and model the motion of objects, biology, economics, and more. From modeling the spread of diseases to predicting stock market fluctuations, differential equations are essential tools in a wide range of disciplines. Learning about them is like unlocking the code that governs the natural world. It's about gaining a deeper understanding of the forces that shape our reality. With differential equations, we can predict the future from the present. By understanding the relationships between quantities and their rates of change, we can extrapolate into the future and make informed predictions about what's to come. In this video, we'll break down the basics, providing a solid foundation for understanding differential equations, explore different types, and solve a simple example. We'll work through the problems step by step so you can see exactly how these equations are applied. Most importantly, we'll see how these ideas connect to real-world situations. We'll explore examples from engineering, physics, and other fields to illustrate the practical applications of differential equations. Differential equations aren't just abstract math. They're practical tools for understanding complex systems. They are used by engineers, scientists, and mathematicians to solve some of the world's most challenging problems. By the end, you'll see how they help us make sense of the world's constant motion. You'll gain a new appreciation for the power of mathematics to describe and predict the behavior of complex systems. Let's get started. Let's embark on this journey of discovery and unlock the secrets of differential equations together. Before we dive deeper into the world of differential equations, let's take a moment to clarify some essential terms. Understanding these fundamental concepts will be crucial as we progress. Think of this as building a strong foundation for more complex ideas later on. At its heart, a differential equation contains a function which represents the unknown we're trying to find, and its derivatives, which describe how that function changes. Essentially, it's an equation that relates a quantity to its rate of change. This rate of change is what makes differential equations so powerful for modeling real-world phenomena. For example, a simple differential equation could be written as dy dx equals sine y. This equation says the rate of change of y with respect to x, denoted as dy dx, is directly equal to the value of y itself. In other words, as y increases, its rate of increase also increases proportionally. Now here's a key point. The solution to a differential equation isn't just a single number like you might find in a regular algebraic equation. Instead, it's a function that, when plugged into the differential equation, makes the equation true. Going back to our example, dia dx equals sine y, the solution is y equals sine c circumflex x, where e is the base of the natural logarithm. Notice that c is a constant. This constant is crucial. The presence of this arbitrary constant means that there isn't just one single solution, but rather an infinite family of possible solutions. Each different value of c gives us a different solution curve. This is where an initial condition comes in. An initial condition is a specific piece of information about the function at a particular point, like y, 0, equals sine 1. This tells us that when x is 0, y is equal to 1. This initial condition lets us find the specific solution we care about by determining the value of c. By plugging in the values from the initial condition, we can solve for c and pinpoint the exact curve that satisfies both the differential equation and the initial condition. We call the solution with the arbitrary constant the general solution. It represents the entire family of possible solutions. And the solution we find after using the initial condition to solve for c is called the particular solution. This is the unique answer that fits the specific scenario we're interested in. So, to recap these ideas: differential equation, solution, which is a function; initial condition, which helps us narrow down the possibilities; and the distinction between general and particular solutions are the foundation for everything that follows in our exploration of differential equations. Make sure you have a solid grasp of these concepts before moving on. Now, let's classify differential equations. Understanding how to categorize these equations is crucial because it dictates the methods we'll use to solve them. We'll focus on two key characteristics: order and linearity. These properties provide a framework for approaching different types of differential equations. The order is the highest derivative present. It essentially tells us the degree of differentiation involved in the equation. Think of it as the highest power of change that the equation considers. It's first order if it's just dy dx, meaning the equation involves only the first derivative of the function y with respect to x. This represents the instantaneous rate of change of y. It's second order if it's d dy dx2, indicating that the equation includes the second derivative. The second derivative describes the rate of change or the concavity of the function, and so on. You can have third order, fourth order, and even higher order equations, each involving a higher level of differentiation. The higher the order, the more complex the relationship being modeled. For example, dy dx equals sine y is first order. It states that the rate of change of y is directly proportional to y itself. d2y dx2 plus y equals sine 0 is second order. This equation describes a system where the acceleration of y is related to its displacement, a common scenario in physics. Order tells us about the system's complexity, reflecting the number of factors influencing the rate of change. Higher order equations often model more intricate and dynamic systems. Next, linearity, another crucial aspect. A linear equation has the function and its derivatives appear simply, meaning they are not raised to any powers, nor are they arguments of other functions. They are not multiplied together or inside other functions like sine, cosine, or exponentials. Each term involving y or its derivatives appears as a simple multiple. For example, y plus 4ye plus 3y equals sine cos x is linear. Each term involving y is a simple multiple, and the equation is set equal to a function of x. Di dx equals sine sin y is nonlinear because the derivative is equal to the sine of y, meaning y is inside another function. Linear equations are generally easier to solve. A wealth of techniques exists for finding solutions to linear differential equations. Nonlinear ones can be much more complex, often requiring numerical methods or approximations to find solutions. This classification helps us choose the right approach for solving, guiding us toward the most effective methods for each type of differential equation. Let's see differential equations in action. Population growth dp dt equals sine kp models. How a population grows faster as it gets larger, classic exponential growth. Newton's law of cooling dt dd equals sine kt tr describes how an object cools toward room temperature. Compound interest dA dt equals sine RA models money growing in a bank account with continuous compounding. Radioactive decay, DND equals sign ln, shows how substances decay at a rate proportional to what's left. These simple equations describe everything from bacteria multiplying to coffee cooling to ancient artifacts decaying. The same mathematical structure appears in many fields, showing the power and versatility of differential equations. Now, let's solve a differential equation using separation of variables. This method works when you can get all the y's and dy on one side and all the x's and dx on the other. Once separated, integrate both sides. This turns the equation about rates of change into a direct relationship between y and x. Integration introduces a constant representing the family of solutions. This technique is simple and powerful for many real-world problems like population growth and radioactive decay. Let's solve dy dx equals sine y with the initial condition y0 equals sine 3. First, separate variables 1y dy equals sine dx. Integrate both sides. 1y dy equals sine dx. This gives ln vertical bar equals sine x plus c. Exponentiate both sides. Vertical bar equals sine e circumflex x plus c equals sine a circumflex x, where a equals sine e circumflex c. So y equals sine a e circumflex x. Apply the initial condition 3 equals sine I circumflex 0 equals sine 3. The particular solution is e equals sine 3 e circumflex x. This step-by-step process, separate, integrate, solve for the constant, shows how we move from a differential equation to a specific solution. Why do differential equations matter? They let us predict the future of dynamic systems. For example, sending a rover to Mars requires solving differential equations for gravity and thrust and drag to plot the exact trajectory. In epidemiology, models like the SciR system use differential equations to predict disease spread and guide public health decisions. These equations turn present data into future forecasts, making them essential in science, engineering, and beyond. They're the mathematical language of change, giving us insight and control over complex systems. Differential equations are everywhere. In engineering, they model vibrations in bridges and buildings, helping ensure safety. In electronics, they describe how circuits respond to signals. In biology, predator-prey models predict population cycles. In finance, the Black-Scholes equation revolutionized options pricing. These examples show how differential equations underpin technology, science, and even the economy. We've explored how differential equations link functions to their rates of change, providing a framework for understanding dynamic systems. We covered key terms, classification, and a step-by-step solution method, from population growth to engineering and finance. These equations help us model and predict the world. Mastering them bridges abstract math and real-world application. By learning this language of change, you gain a powerful tool for interpreting the universe. Keep exploring, there's much more to discover. Thank you for joining this journey into the mathematics of change.